We're moving away from the univariate probability distributions to bivariate probability distributions, because this is a course on econometrics. We want to be thinking about associations between random variables, and thus we're going to take the next step of adding one more random variable in the mix. So we will be talking about the joint distribution as our first step. The definition here goes as follows. If you have a random variable x, our very familiar random variable so far, and a random variable y. Okay, capital Y symbolizes a second random variable we were going to be talking about. So if those two are two random variables, the distribution of x and y simultaneously is going to be called their joint distribution. Again, econometrics is about relationships that are not deterministic, so this is going to be a very fundamental concept for what we do here. Note that we're conveniently labeling the two variables x and y. There's no particular reason why we should be considering this as our dependent variable. For those of you who have done econometrics in the past, this could be x1 and x2. It doesn't really make a difference, but eventually it will be very useful for us when we transition to econometrics to be thinking about these random variables in this notation. The other comment that I want to make is that you could have a sequence of x's, right? So this is the bivariate case, two variables. You could have n variables that you are considering their simultaneous joint distribution. When it comes to values that these random variables take, we are going to use the notation of the lowercase letters that correspond to the capital, to the uppercase letters. So lowercase x is a value for x, lowercase y is a value for y random variable. That's familiar based on what we've done in the past. Each trial of whatever experiment we're considering running, or it's sort of observation that we're picking up from the world out there, is going to be producing those values in pairs in this case. So we're going to be talking about the x and y pair emerging simultaneously. As you can imagine, we're going to be talking about discrete joint distributions and continuous joint distributions. So our first case has to do with a discrete. If x and y are discrete random variables, then the pair is going to be said to have a discrete joint distribution. That hopefully is quite obvious for everyone at this point. And for the discrete case, we're going to be defining the probability functions, or the probability mass functions, as follows. We're going to use the lowercase f notation for that. At this point, this is not a function that is an argument of one variable. There's two variables here, and it's going to denote the probability that the random variable x takes a specific value x, comma, random variable y takes a specific value y simultaneously. That's sort of the idea behind the joint probability function. Following the exposition that we had in the univariate case, we're going to think about the properties of this joint PMF in the discrete case. The first property has to do with the non-negativity aspect of these functions. This f of x comma y function is going, as it reveals the probability that x takes a specific value and y takes a specific value lowercase y, that probability is going to be greater or equal to 0 for all values x comma y that belong in the space of R2. So the real numbers for both x and y random variables. The other property that you can also guess from the univariate case has to do with what do all of these f values add up to if you sum across all possible values of x and sum up across all possible values of y. Well, similarly to the univariate case, the summation of these values has to be equal to 1. Note here that the summation has to happen with respect to both arguments in the function, both with respect to x and with respect to y. Let's use an example here. Let's say that this PMF is defined as follows: f of x comma y is equal to 1 over 42, and in the parentheses multiplied with 2 times x plus y. What are the possible values for x, 0, 1, and 2, what are the possible values for y, 0, 1, 2, and 3. For all other values of x and y, that functional form takes the value of 0. So, how can we visualize this particular PMF? Because of the discreteness of x and the discreteness of y, we can think about creating a table, like a probability table, where on the one axis we're going to list all possible values of x, on the other axis we're going to list all possible values of y, and then inside the cells in this table we're going to be thinking about, well, the combination of of x and y values. So this example here would look like this. So let's say we arrange the x values across the column, the y values across the row, and we start thinking about the entries. Well, originally this is blank, right? So this is filled out for you, but let's think about how these values get calculated. So, for example, here we're going to pick up a value of x equals to 0, and at the same time a value of y equals to 0. If we go in our functional form, that's 0, all of this becomes 0. That's an easy case. Let's say we're going to think about the case where y is equal to 0 and x is equal to 1. So x is equal to 1, that's going to make this a 2, that's going to be 0, 2 multiplied by 1 over 42, that would be 2 over 42. Okay, this is where this value comes in. Let's do the opposite. Let's say y is equal to 1 and x is equal to 0. So that's going to be 1, that's going to be 0, so 1 over 42, we fill in the values. So by repeating all of this analysis, all of the combinations of x and y, you can generate this probability table from the discrete joint distribution. Make sure, and you can do it very quickly here, that these probabilities inside the probability table are going to sum up to 1, because this is the property that we have defined for the joint PMF in the bivariate case. So note again that all of these entries on the table are probabilities, very similarly to the univariate case, and in many ways they can be thought of as perhaps the equivalent of seeing some frequencies in the population of whatever phenomenon you are trying to explore. I'm going to give you an example here utilizing actual data. You can find this in the Goldberger textbook, a course in Econometrics, on page 2. So here's the example from the textbook. We're going to see a table like the one that I just showed you, but with actual data, referring to a little bit more than 1,000 families that were interviewed by the University of Michigan Survey Research Center for particular years in the 1960s. It records information about average income across 2 years and the savings rate, which is the proportion of the ratio of the family savings to the income. This is information that is produced in grouped form, so they're creating essentially bins across incomes and savings rate. And I'm going to show you the table here. It looks like this. Okay, so similarly to the simpler example that emerges from some sort of experiment, this one reflects sort of observational data where you have income bins classified across the row over here, and savings rates classified across the column. And inside the table you can see the frequency at which you observe these particular combinations of income and savings rates. The message here is that you can see this frequency table as a probability mass function, or at least the equivalent of a probability mass function from the population. This is definitely reflecting a sample. We cannot quite possibly collect the information for the population, although sort of census information does get closer to the idea of having the population numbers. But again, I think that's a more practical example where you can connect the notion of the PMF to reality. Going back to the discussion of the discrete joint probability functions, we can establish a few other findings or other properties. So for any subset A that belongs in R2, essentially subsets of values of x and y, we can define the probability that we're going to see a materialization in this subset, right? So the probability that a pair of values falls in that A subset is simply going to be the sum of your PMF values for the x and y pairs that fall in that subset. So what does that actually mean? Here's an example. So you can ask the question of what is going to be the probability that x is going to be greater or equal to 1 and y simultaneously is going to be less or equal to 2. What you need to do in this particular case is pick all of these f of x comma y pairs that fit the bill for this particular problem. So for example, you can start with picking up the value of f1 comma 0. Okay, that obviously fits that particular space subset. Then add the value of f1 comma 1. Okay, yes, x is greater or equal to 1 and y is less or equal to 2. Add to that f1 comma 2 and so on and so forth until you get to the answer that you are exploring. Visually, it's worthwhile looking at the table in parallel. So let's see. What is the situation here, or rather what area of this table does this problem reflect? Well, all of the situations where x is than 1, greater or equal to 1, so these two values are relevant for our problem, for the probability that we're trying to calculate, and values of y less or equal to 2, right? So we're talking about these set of 6 cells that contain all of the information about the probability of having a pair of x comma y fall in that space. So if you do this calculation, this is simply a summation: 2 plus 3 plus 4 plus 4 plus 5 plus 6 divided by 42. That gives you the answer of 24 over 42. Similarly, you can also calculate the probability of a random variable taking a specific value without any consideration over what actually happens with the value of the other variable. So obviously it might be confusing to some of you that I'm listing simply one of the random variables within this expression, right, while we are picking this information from clearly a PMF that involves two random variables. But what we're saying here is that we are not going to care about what is happening in the x dimension. All that we're going to care about is what is happening for the random variable y. Okay, and we're pinning that information to the value of 0 here. So how are we going to calculate this? This is going to be equal to the sum of all of these f of x comma 0 values, because we've pinned y to 0. So y is going to be equal to 0 across all of the values of x. And we're going to sum up all of these f values across x. So what would that be the case? X equals 0, y is equal to 0, x is equal to 1, y is equal to 0, x is equal to 2, y is equal to 4. So the summation here is going to be 0 plus 2 over 42 plus 4 over 42. That would be 6 over 42. So that's all that I have on the discrete case. Let's look at the idea of a continuous joint distribution here and start with the definition. Random variables x and y will have a continuous joint distribution if there exists a non-negative function f such that for any subset of, let's call that subset A, sort of that is sort of pairs of x and y, the probability that x and y belongs in that subset A is equal to the double integral of f of x comma y dx dy. So that's sort of initial sort of definition, or rather the formal definition. Think about the idea that this f function is non-negative. That is something to be expected given what we have learned about the univariate case so far. Now we're looking at the probability that pairs of x and y random variable values fall in a particular domain of R2. and we're going to calculate this in a similar fashion as we did in the discrete case by the equivalent of a double summation sign, which in the continuous case is integrals. So we're going to do the double integral of this f of x comma y function over ranges of x and y. Okay, rather x and y. The f function that we just discussed is called the joint PDF, the joint probability density function of random variables x and y, and it has standard properties that we have explored before in the univariate case and in the discrete case for joint distributions. The f of x comma y has to be non-negative for every x and y in the space of real numbers, and also the summation of this joint PDF across all possible values of x and y has to add up to 1. So this, in the continuous case, is identified by the double integrals ranging across all possible values of x and y, theoretically minus infinity to infinity, and sort of that adds up to 1. In terms of assigning probabilities, falling closer to the definition of what we just established before, let's say you're trying to find the probability that x is going to range between two values a and b, and y is going to range between two other values c and d. This, you can apply this calculation effectively. Take the integral of f of x comma y, first with respect to x for the interval of a and b. Once you have found that solution, do the same thing with respect to y as it ranges from c to d, and thus you're going to have the probability that you are looking for. So let's look at a specific continuous example with a very simple functional form. Let's say that your f of x comma y is equal to c, that's a c, by x and y, is a parameter. So this could have been a number. We're actually going to figure out what that number is in this problem. Okay, but this is like saying 2 times x times y. Okay, so that's the functional form we're going to be using. In this functional form, x ranging between 0 and 4 and y ranging between 1 and 5. And everywhere else in the domain of x and y, you're going to get a functional form, function values being equal to 0. So this particular example is asking you to calculate what is of c. Okay? What is the c over here so that this thing becomes a joint PDF. Remember, for some function to be a joint PDF, it has to a couple of rules, right? These two properties are the things that we're going to be using for this type of analysis. So obviously we want the f to be non-negative, and we want the double integral of this f function to equal to 1. So let's work this problem out by doing a little bit of integration. So we're going to base our analysis on the second property for the joint PDF, and we're going to see what value c is going to allow this expression to become equal to 1. So first thing that we can do is plug in the f of x comma y functional form. That will be c times y. dx dy obviously stay there, and then define the endpoints for the integrals. Okay, with respect to x, the integration is going to go from 0 to 4. With respect to y, it's going to go from 1 to 5, given the information that we've had in our problem. Okay, so let's this integral by sort of considering x first, effectively. So we're going to look at the integral from 0 to 4. We're going to isolate this part over here. What's going to happen is that we're asking simply for changes in x. So we can treat c and y as if they were constant. So this one is definitely a constant. We treat y as a constant. So we're going to pull them out from the integral, and we're going to thus be able to calculate x 0 to 4. Having to worry about c times y. Okay, how do you do this? This would be square divided by 2, evaluated between 4 and 0. Okay, you can do this calculation over here, and I don't believe I'm skipping any steps in this analysis. So this is going to be 16 divided by 2. And now we are ready to calculate the second, the outer integral. We have a constant, that would be 8. That's another constant, c. That 8 times c can come outside of the integral. What remains in here is y, and you can do this integration y squared divided by 2, evaluated between 5 and 1. So you over that c, you make the calculations, you end up with a result for this integral being equal to 96 times c. So at this point, know that this expression to be a joint PDF, this has to be equal to 1. So essentially what we're saying is that 96 times c will have to be equal to 1. So from the second property for joint PDFs, 92 times c has to be equal to this integral. We just developed this is equal to 1. So guess what c is going to be equal to? Divide both sides by 96. c is going to be 1 over 96 if we want this property to hold. And we do want this property to hold, because otherwise this function that we have established here is not going to be a joint PDF. Right? We do care about functions in general in mathematics, but in particular with probability and in econometrics, we want these functional forms to actually be joined PDF, so that is probabilistic sort of these functions, or rather we can use these functional forms for the purpose of analysis of probability models. So now we are ready to plug in c into the functional form. So that c is 1 over 96. Then the functional form is 1 over 96 times x times y. That is a joint PDF in this case. And we can use this joint PDF to make some calculations. Right. So we allowed for x and y to vary theoretically, x between 0 and 4, y between 1 and 5. And we can ask an interesting question. What is the probability that x is going to be less than 1 and y is going to be, value for y is going to be greater or equal to 2? So diagrammatically, if you will, this is sort of the foundation of our joint right? This is sort of the footprint of our PDF, which, if you think about it, is a three-dimensional shape. This is sort of what you see from the top if you were viewing it from the top, and this is sort of the area that we're interested in extracting probability for. How do you solve this? Well, you plug in your f of x comma y into the double integral. You define the exact ranges for the x variable and for the y random variable. You solve this integral. You're going to a number that is going to be probability that x is less or equal to 1 and y is greater or equal to 2. Again, the inequalities here, or rather the equality part of the inequality, does not matter as much because we're in the continuous. To the case, the univariate case that we've seen, if you have a continuous joint distribution, the probability that x is going to take a specific value and y jointly is going to take another value is going to be equal to 0. The PDF does not provide you with probability information for being at a specific point. Rather, you can think about this probability as being rather minuscule, so you need to define it in terms of intervals in the same way that we're defining sort of a probability for a particular interval here, rather than a specific point, let's say the 1, 2 point over here. Think about the fact that you similarly cannot establish a probability for a line within this space. You still have to talk about interval. A line can be considered as an infinite number of points, right? And because we cannot assign a probability to a point, we cannot assign to lines composed of a sequence of points. So the probability, let's say, of x being equal to 2y, so that over here would essentially draw a line within the space of possible outcomes, right? For x and y, that probability would be to 0. So remember that when you want to calculate this bivariate, or even in the multivariate case, you need to be about for x and y or any other random variable that you're introducing in the analysis.